This is a big pleasure to be invited to this. So thank you, Sharon. Thank you, David. I've been working on technology that helps us for many years now, 12 years. And I've sort of always done that from an AI perspective. And very often I was the only AI person in the room when doing these things. And so what was very important to me, that I sort of had to always package things up to make them attractive to AI people, but now I can repackage these things to just show you what we can do in AI for disabilities. And it's also a bit of a story of a journey of learning and experiences that were terribly humbling for me over the past few years that I wanted to share with you today. I also am aware that there may be a bunch of AI people, researchers, students in the room who are interested in AI and machine learning, who are interested in disabilities, but very often may not be appreciative of the fact that there are really hard problems in AI that we can crack on the shell of assistive technologies. And so one thing that we need to understand is that technology that you build to help is really technology for us all. And if you look at the history of some of the most successful technologies, the telephone by Graham Bell was directly inspired by the hearing impairedness of a relative that he wanted to address. Similarly, the invention of the typewriter was not to make life easy for stenographers and secretary. It was to help a motor disabled person with a hand disability to be able to communicate. The first text-to-speech systems that came over 40 years ago were not developed, for you to read your email. They were developed specifically for hearing impaired people, and the technology developers at the time, computer scientists, were excited by that. And similarly, if you go back and look and hunt down the first speech-to-text type work, the inspiration very often was actually driven from helping people, often relatives, sometimes people who were personally affected, into finding solutions. So all of these technologies here, if I were to present them without the disability context, say, oh, these are very useful technologies. But what I want to take you away from here, that developing technology that are inspired or prompted by the needs for having assistive support are actually technologies that always will help us all, because we can all do with a bit of help. And of course, in the following, I want to say there are many forms of disability, and I'm going to focus on a specific one, namely motor disabilities, because that's what simply happened that I work on. We should, of course, acknowledge that there are many other forms of disabilities that can be helped by other forms of technology. So let me start with the basic problem. If you have a motor disability, what typically happens is that your brain and your body sit in something that we call the perception action loop. You have, cells and chemical processes that operate in your brain. And, if you have a genetic disease, for example, this can disrupt their function. Say, for example, Duchenne muscular dystrophy slowly kills your muscles. If you have ataxias, often they have a genetic basis, meaning cells don't function well. You may have disabilities that arise from issues in the spinal cord that are sort of diseases, but often motor disabilities also arise from injury, from having a stroke, from having a spinal cord injury, for example, from losing an arm or a limb. So there are many reasons why this loop of perceiving the world and being able to act in the world are actually cut open, and you cannot freely do one or the other, because somewhere in this loop there is a disease or a trauma that prevents you from closing this loop. And so what I really want to talk about is how we can think about human restoration of the ability to move in one way or another, and that actually requires to talk us about interfacing. How can I interface my mind that has intentions about being wanting to act out things in the world, to interact, to physically act on things if I'm being impaired. And what I'm showing you here is a person who's wearing, who's lost an arm, and he is wearing a technology for an arm prosthetic that's around 650 years old. It was invented by a German knight, and effectively it's what happens there is that this person is wearing this claw, and there, so you can see that this claw can be opened and claw closed by some form of steel cable. And what that steel cable does, it goes to the other side, to the other shoulder, and by basically lifting the shoulder up and down, this person can open and close the claw. Now, this may look to you like very primitive technology, but I will show you it is very powerful technology. In fact, technology is so powerful that it beat a lot of AI and bioelectronics-based replacements. And I'll get to that in a second. But first, I want to tell you about one of the most humbling experiences of my life, and that's participating with the team in the Cybathlon. So the Cybathlon is the Bionic Olympic Games that has started in Switzerland in 2016 and were conducted also in 2020 during the pandemic in each individual athlete's home. And if you're looking at the spectrum of disability in the motor level, you have, of course, the Olympic Games, where you have people with full biological function, and then you have the Paralympic Games, where people have sort of limited abilities, say because they're missing some form of limb, and so they still retain a lot of the biological function. And then we're going all the way to what the Cybathlon constitutes, and it's an international competition that in 2020 attracted 65 teams from all over the world, on all 4 major continents, that are basically technological solutions where you do require electronics. They need some form of control you can talk about. They need some form of artificial brain to interface with the user and empower them. And so here you see, for example, the leg exoskeleton that can help this young person who is paralyzed from the hips downwards to stand up and walk. And here, this is Jonathan, a very inspiring person I've been working for the past 2 years, who was interested in having brain-computer interfaces and using them in the Cybathlon. So the Cybathlon is a competition that basically involves many different forms of races, just like in the Olympic Games. Here you see our team, where we have students from our biomedical engineering degree who basically volunteered to participate in this project. And so they did a 2-year-long project in developing assistive technologies, a wheelchair in this case. And here you see Shivash, who's actually a spinal cord injured person and who we recruited through basically pasting ads and contacting patient organizations. But then he had a management career. He worked in hotel management and then realized the real thing for him forward is to abandon his career and engage in biomedical engineering to build better solutions for people who have disabilities like him. And he went on to do a full PhD and is now a researcher in the field. And that was terribly inspiring. So just to showing you just random pictures from the races. So here you have spinal cord injured person being assisted by this robotic leg to walk upstairs. So the Cybathlon is not, who is fastest from A to B. You need to solve real world challenges. Here you see us at the wheelchair race that we competed in. It involves things like cycling on a wheelchair for people who are spinal cord injured. And this so-called functional electrical stimulation cycling works that you're stimulating the leg muscles that are still there and basically get the legs to pump so the cyclist can walk, can cycle. And these type of sports are very important for people who are lower limb paralyzed, because effectively they don't get the cardiovascular exercise. And it can be shown that people who are using these type of fast bikes can substantially, and I'm talking here 10 to 15 years, extend the life expectancies because they often suffer from cardiovascular problems. And as I'm going to show you a bit later, we've developed here a whole range of reinforcement learning technologies that optimizes the stimulation pattern. There are, of course, also other races, people who are, for example, missing legs because, for example, they've been born without or they had accidents, and people competing in races that, for example, involve manual skill. But again, here, the interesting thing about the Cybathlon was it involved walking up ramps like you find in the real world, having to master obstacle courses like you can find in any garden, or, for example, in this case, folding cloths and cutting a baguette, for example, were part of the arm prosthetics race. And it is in this arm prosthetics race where all, in 2016, every single bionic, smart, logic, AI, whatever prosthetic was beaten by this gentleman who was Dutch and who was simply having this claw that they were controlling with the contralateral shoulder. And that was a second humbling moment for me, because it realized that, you know, all this technology doesn't really help if the interface doesn't really work well. And so the challenges are really, how can we better interface humans with the technology that is meant to assist them in their movements? And very often, if you look across the spectrum here, you find that for certain photomotor disabilities, there are no devices that can help you, or that they come with a very high cost of aftercare. Sometimes these technologies are very complex to set up and calibrate. It cannot be done by the end user themselves. They need assistance. They may even in some cases have to have an engineer come and set it up, even for daily use, for example. They're very slow at decoding your intention. So you don't have a lot of degrees of freedom you can control. Even grasping or making a move is very slow and cumbersome. They're very slow from the moment that you want to do something, them actually starting to execute that. And imagine if you're able-bodied listener to my talk, if imagine you would be typing and every keystroke that you type on keyboard does not appear immediately on your screen, but takes 1/10 of a second to appear. You will go mad if that happens. But this is the type of challenges people endure. Very often, these type of assistive technologies, you cannot use immediately. You have to go through weeks, if not months of training. And that requires psychological stamina, as well as appropriate support for undergoing these training. And not surprisingly, a lot of assistive technologies, and especially prosthetic technologies, have very low adoption rates. And what I mean by adoption rates, assuming that you're lucky to have health insurance or NHS that provides you with this assistive technology. Very often, for example, prosthetics are abandoned 3 to 4 months after they've been prescribed and fitted to an end user, because they basically find it too cumbersome and not intuitive to use. And they prefer to use very simple, either cosmetic prosthetics, for example, in the case of hand amputees, or these mechanical devices. And ultimately, all of these devices that help you with moving don't feel like they're embodied by you. They're not a part of you. They feel like external tools that are supporting you, but there's no natural relationship. And we think that's a main driver for the lack of adoption of these technologies. And I wanted just to show how dramatic this situation is and how little we actually understand the problems around here. So if you look into any textbook, they will tell you that, for example, for the hands, the two most important hand movements are the power grip and the precision pincer grip or grasp. And this has been assumed to be always the case, right? And then it's actually for 300 years, people have been telling you these are the two most important hand movements. So when you're building prosthetic technology or technology to rehabilitate people who had a stroke, you assume that this is what you should be able to rehabilitate. And it then turned out that if you actually put on sensors to actually see what hand movements do people carry out in their daily life, and we did this from 2009, from 2011, we actually found that the precision pincer grip does not appear a single time in an average student who spends a day in our studio flat wearing our sensors. For whatever, they just don't use that grip. They may do other things, they may hold a pen, but the precision pincer grip does not appear a single time. And yet you're rehabbed on that, prosthetics are developed based on that, but we actually didn't even appreciate what actually constitutes natural behavior for interacting naturally with our environment. So the first thing that we did is set up a whole program of doing experiments in the wild and actually measuring what are the movements that we actually need to do in daily life. And this is very technological and looks like this, where you can basically see here the type of experiments you conducted in able-bodied people first, where you can see here the skeletal reconstruction of the person having breakfast. We measured what they were looking at, where they were looking at, we were measuring what their fingers were doing. And we took all this data together and built a ginormous database that we called the human ethome database. You may have heard about the human genome. Ethome comes from ethology, so behavior. So this is the equivalent of measuring all your genes. We measured simply all of people's behavior. And when you start doing this, you realize a few things. that if you want to discover what are the most important hand movements of a person, there's no trivial way of doing that. And for those of you with a machine learning background, we basically needed to develop methods that can do time series clustering. So looking at the movements of the hand and tell us what are the hand movements that naturally occur. And then you realize that, of course, a hand movement can be small or a hand movement can be large, but it's still the same hand movements because, say, you grasp a cup here or there at the bottom. So you need to develop now methods for clustering time series that are timescale invariant and amplitude invariant. And this is a technical bit, forgive me if you're not technical, but this is actually a non-trivial problem that really no one cared about in the machine learning field or in the engineering community in general. And so we start to develop methods for that. Once you discover what the basic hand movements are, and by the way, believe it or not, these are the three most important basic movement patterns we see in daily life activity of the hands. These are basically slightly different forms of grasping movements that don't look anything alike that precision pins grip. You can then basically start thinking about robotic control algorithms that can basically execute this thing. And then the first thing that you then realize is then that robotic hands are actually built for grasping things. And so a lot of prosthetic hands that are robotic are also made for grasping things. But a lot of the time, actually 60% of your time, if you're able-bodied, you're not using your hands to grasp things, you're using them to manipulate objects, to do something with them, for example, like texting. And then you realize that even the robotic algorithms that have been developed are all made for grasping, not for in-hand or manipulation of objects. So this triggered a whole set of projects that we did in the domain of control in robotic systems that allows us to do what you're seeing here, now basically text on a mobile phone. And what I should add here, these are not movements that are executed by the robot alone. These are decoded movement for prosthetic hand use. So we're decoding the intention of a person. The next challenge, and again, this is slightly technical, is how do we do this brain-computer interfacing? How do we decode information? And for the past, literally since the 1990s, when these first brain-computer interfaces appeared, we've done it always in the same way. We've basically had some brain signal that we read in, and then we translated that brain signal into some form of movement command. And so that's a direct mapping from brain signal to movement command. And if you're an AI person, you will recognize you can solve that by supervised machine learning. And there are many ways of doing that. I'll let you choose. But actually, the problem is when you're getting brain data, you're not getting the data of the whole brain. You're just getting a very limited amount of very noisy signals. So this is sort of a very difficult thing to do because you need to decode the whole movement just from that little bit of brain activity, and the movements can therefore not be very complex. So then the next realization was actually movement is very predictive of movement, again, if you're able-bodied. So the idea is that if I want to grasp, for example, a cup, almost everything about my grasp is predetermined, how my fingers open up, all the individual degrees of freedom of my finger, and how they then close. So if I know what movement you're executing, I can almost, play it back. And then comes the idea that, well, then I'm just a pilot. I'm a passenger in a car that goes on its own. That's not what we want when we build assistive technology. We want people to be in charge. And so this required us to build models that we call sort of autoregressive models with exogeneous inputs. For the non-technicians, whatever that is, it's slightly more complicated than the standard approach that everyone pursued, where you basically use the past movements to predict future movements. And then you use that bit of signal from the brain that you can get to basically steer the movement. So most of the grasping movement towards the cup is not controlled by the brain signals. It's controlled simply by how the hand would naturally move. And only when the brain signal comes and say, grasp it or release it or do something else with your hand, only then you need that bit of information to change how the dynamics of the prosthetic hand movement evolve. And so with that, you can find solutions. And again, I'm just dropping this slide in. It's a very technical slide for those with you with an AI machine learning background. So what we needed to do is to build an autoregressor that can deal with additional control inputs, and it need to be very data efficient. So data efficiency is a big problem in AI because the standard approaches require ginormous amounts of data. That's very easy if you have large, so to speak, social media type data sets. That's what a lot of AI development is made for. Make social media companies happy because they pay for a lot of AI research. But if you want to go into a patient or end-user centered domain, you need to become very data efficient. You cannot get a person who has lost an arm to spend hours or days of training the machine learning algorithm with data from their movements. You need to find something very efficient. And so we developed something called Gaussian Process Autoregression with exogenous input, and basically built a novel form of control of the hand that gives us more degrees of freedom for controlling the hand, actually 22, as many as your actual hand. And you've seen these examples of this, that you can now even text with this type of prosthetic interface that basically just reads out muscle commands, so muscle signals like normal prostheses, but gives you full flexible control of the hands. So just on a slightly other note, because we're talking about data and the challenges of data, there's another big challenge, and we've mentioned that already previously in the discussion, that we want to preserve the privacy for things. So in the Cyberthon, we had also a competition where people who were fully paralyzed, who couldn't move at all below the neck, needed to sort of interact with the computer. And so they set up a video game effectively that people had to play interactively to give people a sense of agency. And so typically you put on these type of EEG caps. So these are, they capture these brain waves, and you need to collect brain data. And so here in the AI methods, deep learning has become very popular in the field. But the challenge with this deep learning is I need loads of data from you. And that makes it hard. So what would be easier if I can get data from loads of different brains and train my AI on all these different brain data. But now brain data is extremely intimate. It's extremely private. So to overcome the challenges of this, we basically needed to recurse to an approach that has been developed in AI over the past few years, so-called federated machine learning, where the idea is you don't get the data and train it on your machine, but basically you build a model and then you send this model on a trip, and this model then goes to the different end users, for example, and learns from their data how to improve itself. And then it travels back and goes to another user. And that little model does not know anything much about your brain. It has just learned how to solve this specific decoding task slightly better. And so this idea that the model travels in the data space is what we call federated machine learning, and there are various ways of achieving that. And we have just launched or concluded a major international competition trying to get the machine learning community to engage in building these privacy-preserving methods of training with very private patient data assistive technologies, in this case, doing EEG brain-computer interfacing. And we had some fantastic entries. The most interesting thing here, the winning team, it's a hardcore machine learning team. They know nothing about assistive technology. They found our competition exciting, and we are presenting their results, and they're going to present it how they cracked this competition at one of the world's largest AI conferences next week. So let's talk a bit more about disabilities and how we can help them and how AI can help them. AI can also unlock ways of interfacing people that basically were not accessible before. So one of the most basic things that I learned from universities is that, using my own studies, was that eye movements are very special. So your eyes are constantly in motion. They're very predictive of what you want to do. You can, if you interact with a person, tell a lot about how they're looking with you. But very interestingly, the ability to move your eyes is retained even if you lose the ability to move other parts of your body. That's because eyes are more or less directly plugged into your brain. Different form of diseases and even trauma, such as amputations or stroke, do not affect your eye movements as much as your other abilities to move. So I had the simple question: why are we not doing more eye movement-based assistive technologies? And they've been around for many years now, but why are they not so powerful? And so we investigated this a bit. And so I want to show you first a picture here. So you see a painting by a Russian master, and I can now ask you different questions about this painting. So I can ask you, for example, how old are the people? And then your eyes will move over this picture and paint a pattern that looks, for example, like that. I could ask you, how long has this man been away? And then your eyes wander over this picture and make a different pattern. And this has been known for 60, 70 years, that, so to speak, different mental states, different questions you're asking about this picture result in different patterns of eye movements. And that's called psychology. But we're engineers, we want to build solutions. So what we want to do, and we're AI engineers, so we want to build data-driven solutions. So the question is, can I invert this process? If I know how your eye movement patterns look like, can I guess what you're thinking about? Or at least for the purpose of movement-centered assistive technology, can I guess what type of actions you want to execute? And so the first thing that we did is build technology. So this is a system that a human user is wearing on their pair of eyes. And what I'm showing you here is the video from their own perspective. And you see here a fun circle jumping around. That's actually where the user was looking at that instant. And we can now, in live stream, using very straightforward deep learning technology, decode what object they're currently looking at. That's great. But then also from how they're looking at this object. So are they looking inside the cup? Maybe they're just inspecting what's inside. Or are they trying to grasp the cup, so looking at the handle? We can start decoding what action may a person actually want to intend with this object, and basically translate that intention generated by the eye movements into physical action. So we developed this project. We called it the Enhance project. And it's basically consisting of a robotic arm system that can move your paralyzed arm effectively to the location where you're looking, and then a robotic glove. You can buy that glove that can basically actuate your hand. The key thing here is not, however, getting you to move. Robotic mechatronic technology has moved very far, but we were interested in how can we now use eye movements to interface the system. And we applied this both to paralyzed boys with Duchenne muscular dystrophy, as well as people who are basically paralyzed on one half of the body due to stroke. So very different forms of disability, very different age groups. And the type of technology I'm showing you is very different from the prosthetic technology I showed you, because people have a limb. It's also not an exoskeleton in that sense, because it's not applied to the legs, but it is applied to the upper limbs, to the arms. So this is our project that between getting your arms with an exoskeleton to do what you want to do. And long story short, we then implemented the system. And here you see Peter. He has ALS. He's 59 years old. At this point, this video is now 1.5 years old. He is fully paralyzed in the hand of the arm. He has some minimal postural control of his neck. And this is him using this robotic technology. You can see how his wrist is attached to the robot. He's wearing the glove. And he's basically now picking up an apple and putting it into a bowl as an example. What you don't know is that Peter entered my lab 10 minutes before this video was taken for the first time in his life. His wheelchair was driven to this thing. We strapped him in. And this is effectively 1 to 2 minutes after first time use. And because our system simply analyzes his natural eye movements that are reflective of intention, the system just goes off and starts decoding what he wants to do. And that's what I call, so to speak, a natural form of interface. Where does this eye tracking actually come from? Well, it stemmed from the fact that in 2010, I was a very poor junior faculty who had virtually no startup, and I wanted to do eye tracking experiments. And at that point, I realized that if I want to buy a professional eye tracking system that can measure eye movements, it would cost me £25,000 to buy one. But I also realized that if I'm smart about it, the only reason why I need such an expensive system is because I need very fast cameras, because your eyes move so quickly. So what we then did is we went out and looked, are there sort of any form of other cameras out there that are sort of actually quite performant, but maybe really crappy because they're webcams. And we discovered that the PlayStation cameras were actually very fast. And if you can hack them and put some smart signal processing on them, so basic machine learning, can you do eye tracking? Turns out we can. And we can actually build a system that rivals in almost every metric that of a £25,000 system. So that's what I call frugal engineering through the use of AI. You use crappy hardware with very smart software versus very expensive hardware with very dumb software to solve the eye tracking problem. And so this was one of the first examples that we then did with this user who cannot move. We do the eye tracking, and we simply got him to play the video game Pong. And so that sounds very intuitive. Basically, his eyes control where this bar go. And we had the question, can we build an interface and a calibration procedure that allows people to use that? So, we got a bit of publicity for that at the time. And then we organized a science exhibition here at Imperial College. And so we basically put up these booths. There's basically this thing where you stick your face in, the system recognizes that your face is there, starts automatically calibrating. That's where the intelligence comes in. And then we had over 2,300 people step up to this device, no assistant, no one there. People can just walk up to it and put their face in. The system calibrates itself in 15 seconds. And then people got to play for 60 seconds the Pong game. Turns out, 70% of people were able to play on first-time use in their life. That's 15 seconds after the first time stepping up to this device, they were playing the game, and on average managed to return 8 to 9 balls. So this just shows how intuitive this technology can be if you use signals that are sort of very evident. And so that was the real big problem that held back a lot of assistive technology based on eye tracking. That's what we call the Midas touch problem. Remember King Midas, everything that he looked at turned golden. So that was the problem with eye tracking. Whatever you looked at, you would basically, doesn't mean that you want to interact with it, you might just want to look at it. And that limited a lot of these technologies. But basically by developing these eye technologies, we were also able to apply this in different domains. So for example, people used eye tracking before to drive wheelchairs by basically putting a computer, a laptop here, and basically you then had to look at different regions of the computer screen to steer your wheelchair. And I thought, that's crazy. Why do we want to do that? I don't want to look at the user interface to decide where I'm going. I just want to look ahead and basically look where I want to go. And the system should work out that I want to go somewhere versus just staying seated somewhere. And so we call that what we called a zero user interface technology, because you're just looking out into the real world. And this is how it looks. That was the version Mark 0. So this is a student of mine, Kirabin, and we won the Blackboard Design Award for this, for assistive technologies. There is basically an eye tracking bar here, so you don't even need to wear a pair of glasses anymore. And he's having a very normal conversation. And basically, sometimes he looks at the floor to steer whether to go left or right. And the system decodes that he's basically looking, making navigational eye movements, and then steers him that way. And this is not running on rails or in a prescribed way. That's a very natural interface with very low cognitive load. That's just the coding scheme. And then we took it to the next level. So we we decided, well, actually, when I walk from A to B as an able-bodied person, I'm not constantly controlling my steering where I'm going. I basically more or less decide I want to go to this thing. So what this meant to us, we don't want to build assistive technology that, so to speak, works out the low-level commands. We want an assistive technology that works out what's your high-level intention, what your cognitive intention is, and then translates this command. Okay, so again, you pick up a bunch of students and you pick up a bunch of interested end users. This is Tom Nabarro, with which we've been working for the past 4 to 5 years. He's a software engineer at Intel. He's also completely paralyzed from below the shoulders. And his very limited ability to move his hands, but not his arms, for example. And we basically built a self-driving wheelchair, just like a self-driving car, but for indoor use. Very different problems from driving in a car, because things happen at a lot closer range. There's very different things that happen in the house. There are cats, there are kids, there are toys on the floor. So you need to build appropriate different system from that of a self-driving car. And so that's the Mark 1 system. So first we show you here the self-driving wheelchair we built, and this can work in arbitrary environments. It has the LiDAR, so as it's going along, it's using SLAM. That's a technology that builds maps of unknown environments simply from camera data, nothing special. We can then pair that with a robotic control algorithm that allows, for example, this wheelchair to recognize as an obstacle and then drive around the person. Okay, so we have a self-driving wheelchair. Great, but again, you don't want to be a passenger of your life. You want to be an agent of your life. So we needed now to pair that with intention decoding. And here we've been basically setting up part of our lab in Tom's house, somewhere in the depths of Middle England, where we ported all our computer technology. And here you see Tom, and I'm just playing back, how he's basically wanting to go to a table on the opposite end of the room. The system recognizes that he wants to get to a table. And so now the system starts driving him. There are obstacles arising in the room, and the system still takes him there. And he can have a conversation, look at other things, do other things, because basically the system now knows he wants to go there. And if he wants to change his mind, he can look at another object that he wants to go through, and the system will recognize he's going with the object and taking him there. And so we won the Mobility Unlimited Challenge Richard's Discovery Award for that. That's another end user we've been working on, Paul Moore, who actually has an assistive technology company. And I don't know why the video stopped, but he's been basically using this in his corporate office spaces, which is in a shopping mall, and using this technology there. So I've mentioned at the start the challenges that we have in the field of human interfacing, so to speak. And what I want to tell you is that you can find very cheap solutions if you don't go the threaded paths. Eye movement, eye tracking is very cheap and cost effective. We built eye tracker for £20. That was in 2010. We made everything available publicly. I gave a TED talk, and all of a sudden, all these eye tracking companies could also produce very cheap eye trackers. So we don't have to do the eye tracking ourselves anymore. I showed you the eye tracking can do calibration in minutes, not longer. We have a very fast decoding rate. You can control the endpoint of your arm in a room. You can control grasping. You can navigate. There's very low latency. So the system starts moving as soon as it detects the intention from your eye movements. That's 10 milliseconds. So if you operate this robotic technology, for example, it really feels like magic because it's instantaneous. You don't feel a delay like with many other technologies. The training times are very low. With the wheelchair, in under 30 minutes, you're easily underway. And with the arm-based technology, it's often under 5 minutes. We don't know about the adoption rates because we need to take this technology forward. So I much enjoyed the keynote before because a lot of the challenges we've seen there, we've seen here. And we believe that if you can make things intuitive, because they feel natural to people, fast, non-latent, with very low training times, then you will also get embodiment. And so we've been working with both philosophers in cognitive neuroscience, scientists to think about how can we overcome these barriers to actually embody assistive technology, to make it part of us, not something alien. And this is just stats that I'm going to skip, just to show you how much cheaper the eye tracking technology is. Our eye tracker costs is GT3D, costs 10 to 20 pounds to make. That's the EG system I showed you earlier that costs roughly £10,000. And if you look at the really fancy stuff out there that gets a lot of the attention, this is people who have a brain chip implant and control a fancy robot arm. We're talking easily $100,000, $150,000 cost. But actually, the ability to decode a lot of information is still the most if you decode your eye movements. And similarly, if you're looking at setup times, so how many minutes or hours you need to invest in get to go with this technology, then you'll find that you'll easily spend hours for just a single trial like this with this paralyzed lady being able to drink. What you have not seen usually in these news reports is that they spend 6 hours plugging things in and calibrating things. Even EG takes, if you've done properly and calibrated properly repeatedly, can take hundreds of minutes times of work. And with the eye tracking, you can do it much faster. So this is basically then my outcome of my lessons, that if you do engage with the technologies, and you see Kevin, our prosthetic arm user from our Cyberphone team that has then benefited from all these insights that I spoke about at the start of using smarter technology in the hand, you can give him degrees of freedom that were not possible before. Here, by the way, you see the very small residual muscle movements that our sensors capture or have to capture to then give him the ability to do fairly complex daily life tasks. And of course, I'm the guy giving the talk, but you will see that we actually have a whole team of researchers that contribute to that. We have computer scientists, engineers, we have people who come from medicine, basically want to engage in this journey of doing something meaningful in giving people agency. And some of these may or may not have disabilities. I'm not going to disclose that, but I think it's important to appreciate that it's one of the most humbling experiences to see how you can give people the ability to act again, and how transformative it can be if you apply your technical skill to something immediately useful for somebody. Thank you very much.
Thank you very much, Aldo. That was so enlightening. That Cybathlon seemed fantastic. I'm really interested in finding out more about that. I love the idea that the winner isn't the person who's the fastest, but actually it's solving a social need, a personal need. Yeah. I think that's great. I think that's a wonderful thing. I really also like the frugal AI the idea that AI doesn't have to be expensive to work, or that you don't need to spend thousands to start researching or to start trying to solve a problem. Especially when we heard from Kathy earlier how the majority of people who do suffer from disabilities are actually living in poverty. So to be able to find ways that we can use research frugally but still be able to find real solutions to help them, I think is brilliant. There's people saying how amazing the talk was, and the feedback is fantastic. But thank you very much for your time. I really, really enjoyed that. I've enjoyed the whole day, actually. So thank you to everyone who's been part of the whole day, for being involved, for being part of the panel, for asking questions. If you want to connect with Aldo, obviously his details were on his slide. But obviously you can also just get in touch with me, and I'll be happy to pass on any questions or any details of any of the panelists. We are a little bit over time, but it was worth every minute for that really informative talk. So thank you very much. There's feedback from people saying how amazing it is to see how far text can go to help people with different needs in daily lives. So thank you. And I do think the big takeaway from today is just making sure that people who have these lived experiences are included from the very start, so that the solutions that we try to find are ones that are actually needed. So thank you, and have a lovely evening and take care. And tomorrow I do believe is International Day of Disability Recognition, so please keep this in mind, and if you also did enjoy this, please do share it on social media, on Twitter, and we will be recording this event. Well, this was recorded, it will be put up on YouTube. So again, thank you very much and all the best.